Center for the Ethiopian Educational Information and Communication Technology presents Educational Satellite Television Programs.
Hello, teacher. Hello, students. Welcome to today's lesson on thermodynamics. Previously, we introduced the second law of thermodynamics. Today, we will be continuing on this topic by examining the concept of heat engines. If you are ready, we will begin. I am sure you are familiar with the concept of an engine. Students, when you picture a working engine, most of you will immediately think of a vehicle like a car or truck. However, the definition of a heat engine varies slightly, and it includes objects which are not necessarily used in vehicular motion. A heat engine is defined as a device designed to do useful mechanical work. This work is usually accomplished by taking energy from a hot body called a heat source. Based on the second law of thermodynamics, we know that it is impossible for all of the heat energy to be transmitted from a cold body to a hot body. If this were the case, the entropy of the system would decrease, which contradicts the second law. Thus, the second law of thermodynamics could be stated in a different way. The complete conversion of energy from a hot source into work is not possible. However, if a small amount of energy is allowed to flow into a colder body, it is possible to offset the decrease in entropy of the system. This is accomplished by using a heat sink, which is defined as a body which absorbs heat from other bodies with which it is in thermal contact. This will limit the overall efficiency of a heat engine, since one body is expending heat energy at the same time the heat sink is absorbing it. The theoretical maximum efficiency of a heat engine is only 50%. Let us examine some examples of heat engines. To use the obvious example, this car engine generates heat from the fuel, which it then converts into work. This, in turn, is partially absorbed by the heat sink. Students, let us do an activity. Consider what would occur if the heat sink in a car engine was to fail as it was being driven. What would happen to the engine?
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, everyone. I'm sure you had no trouble answering this question. To put it simply, the engine would break down. With no colder body to absorb the heat being provided by the fuel in the car, the temperature of the engine will increase. Because not all of the heat can be converted into work as per the second law of thermodynamics, the heat is instead lost in the system. Eventually, the engine will be too hot to operate, as this heat energy will transfer to components of the car which must remain at lower temperatures to function. Essentially, its efficiency drops to zero. For many reasons, we want to ensure that heat engines run at the maximum possible efficiency. A measure of the efficiency of a heat engine is determined by considering the energy input and the useful energy output. Thus, efficiency is equal to useful work out divided by total work in. The energy into the engine is expressed as QH, and the useful work is represented by W. Thus, we may express our equation as efficiency equals W over QH. If we consider the law of conservation of energy, we can express the efficiency in terms of energy to the cold sink and energy from the heat source. Therefore, QH is equal to W plus QC. Finally, to determine the useful work produced by a heat engine, we may use the equation useful work out equals energy from the heat source minus energy to the cold sink. To apply this logic to our initial equation, we may simplify our calculations as follows. Since efficiency equals the useful work out divided by the total work in, and work is equal to total work in minus useful work out, then we will eventually arrive at an equation that states efficiency equals 1 minus useful work out divided by total work in. In physics, efficiency is given the Greek symbol eta. The maximum theoretical efficiency of a heat engine is the difference in absolute temperature between the heat source and the heat sink. This can be represented as maximum efficiency equals the absolute temperature of the heat sink, Tc, over the absolute temperature of the heat source, Th. Let us now try to solve some more problems related to efficiency. Are you ready, students? Let us assume this diesel engine receives a heat input of 200 kilojoules. 75 kilojoules are transmitted to the heat sink. What is the efficiency of the heat engine?
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Welcome back, students. This was a fairly simple problem, so I am sure you had no trouble. Solving this was just a matter of substitution into the correct equation. So, efficiency is equal to 1 minus heat entering the sink over heat from the input. Thus, the efficiency of the diesel engine is approximately 38%. Good job. Now, let us determine the maximum possible efficiency of the diesel engine. If the absolute temperature of the heatsink is 225 degrees Celsius and the absolute temperature of the heat source is 450 degrees Celsius, what is the maximum efficiency? Please begin.
Students, let's get ready. Begin. Time's up. Let's get back to our lesson.
Hello again, everyone. I am sure you found this activity to be similar to the last. Our first step in this problem is to convert our measurements to Kelvin, since we are dealing with absolute temperatures. So, the heat sink has an absolute temperature of 498 Kelvin, and the engine has an absolute temperature of 723 Kelvin. Once again, we substitute our values into the equation. Once resolved, the maximum efficiency of the diesel engine is 0.69 or 69%. That is all the time we have for today. We have learned about heat engines and how these can be related to the second law of thermodynamics. I trust you found this informative. Until next time, thank you, teacher. Thank you, students.